So let's start. And today in this talk, I will talk about ice closed subcategory of module categories. And this video is a recording of my rehearsal of the talk I will give tomorrow in Kyoto Representation Theory Seminar. And so let's start. So this talk is based on my joint work with Arashi Sakai, master course student in Nagoya University. So let's start with introduction. So throughout this talk, we will use the following setting. So K is a fixed field, and lambda always denotes a finite dimensional K algebra. And algebra is possibly non-commutative algebra, but is finite dimensional K vector space. And mod lambda denotes the category of finitely generated right lambda modules. And this is an abelian category. And in the representation theory of algebra, we are mainly interested in this category, the small module category, or some related category like derived category of this mod lambda. And the motivation is that we want to study subcategories of mod lambda. Instead of investigating mod lambda itself, but we consider subcategories. And there are so the precise meaning is that more precisely we want to classify certain good subcategories of mod lambda. And so there is two words which are not defined, and so I will explain. So by also this is 2 and this is 1, and by certain subcategories, the typical example of certain subcategory is subcategories which are good in the sense that they are closed under taking some operations. Operations like taking direct sum and taking submodules of modules contained in that subcategory, or quotient modules, or taking kernels or co-kernels of maps between that subcategories, and so on. So there are many combination of these properties. So and in the representation theory of algebra, so particular class of subcategories like torsion class and wide subcategories, which I will define later, have been investigated. And by classify these subcategory, we mean that we want to establish a bijection of the following form. So we want to classify certain subcategories, and we want to make a bijection between these subcategories and certain modules, good modules. And of course, considering modules is easier than considering subcategories. So by establishing this kind of bijection, we can say that these subcategories are classified by certain good modules. And there are many works of this kind of study, a study of subcategory or classification problem of subcategories of mod lambda. And I will I will introduce some old and recent results. A subcategory T of mod lambda is a torsion class. And maybe this was introduced by Dixon in 1966 as a generalization of torsion modules in the category of abelian group. And T is a torsion class if T is closed under some operations, so closed under quotients and extensions. And I will uh, later explain what this exactly means. But so torsion class is defined by these conditions. And there are many results about torsion class. Now, for example, in the quiver representation theory and the theory of tilting modules or planar butlers theorem gives classification of torsion class, and so there are many results on torsion class, and this is very classical object in the representation theory of algebra and related to many areas by considering path algebra or preprojective algebra of linking type. And another class is a wide subcategory. So a subcategory W of mod lambda is a wide subcategory. And this terminology is probably due to Hovey's paper in 2001. If it's closed under taking kernels, co-kernels, and extensions. And this is the same as saying that W is extension closed, exact abelian subcategory. So it's extension closed subcategory, and W is itself abelian category, and the embedding is an exact functor. So there are two typical example of subcategories, typical class of subcategories which have been attracted an attention in the representation theory of algebras. And today's topic is ice-closed subcategories, and this contains both torsion class and wide subcategories. So I will give a definition of ice-closed subcategories. A subcategory C of mod lambda is an ice-closed subcategory, or I simply say it's ice if C is closed under ICE operation. So I is images. So taking images and closed under taking co-kernels and closed under taking extensions. So it means that C is closed under images if for every map between objects in C, its image F also belongs to C. And closed under co-kernels is similar. So for every map F between objects in C, its co-kernel F also belongs to C. The third condition is that for every short exact sequence of this form with these left and right term belong to C, then E also belongs to C. So it's closed under taking extension of modules contained in C. And so this is the main object of today's talk. And so if you remember the definition of torsion class and wide subcategories, it's easy to check that every torsion class and wide subcategory is IC closed. So every torsion class and wide subcategory is ICE. So why? So it's because since, for example, for torsion classes, since torsion class is closed under quotient modules, so if we have this map, then there is a surjection from C1 to image F. So image F is a quotient of C1, so it belongs to C, since C is closed under taking quotients. And similar for co-kernels, and closed under extension is already contained in the definition of torsion class. And for wide subcategories, so image F is kernels of co-kernels of maps. So image F belongs to C and co-kernel F also belongs to C, since wide subcategory is closed under taking kernels and co-kernels. So the rough image is that there are torsion class and there are wide subcategories, and these two classes are there are many works, many papers which study torsion class and wide subcategories. And actually, these two class of subcategories are closely related. So, for example, in good case, there are bijection between torsion class and wide subcategories. But so both of these subcategory is ice. So ice subcategory is um, unifies torsion class, both torsion class and wide subcategories. And ice cross subcategory is very recent object because um, it's new concept which I introduced in the in in the last year. So so actually the if one define certain class of subcategories, then it's a natural desire to classify these subcategories. So how many ice cross subcategories does mod lambda have? So it's very natural question. And today's aim is to achieve this. So I want to classify ice cross subcategories of a given module categories. But uh, so we so I will use this strategy strategy. The strategy is to use a projective generator of an ice cross subcategories. A progenerator is a certain module I will define later, and it's a kind of invariant of this subcategory. So categorical invariant. So I want to classify ice cross subcategory via this invariant. And so here is definition of a progenerator. So let C be an ice cross subcategory, or maybe it's enough to consider extension closed subcategory of module category. Then we say that an object P in C is projective in C. If the X group PC, this X group vanishes. So if a usual projective modules belongs to C, then it's projective object in C. But in general, there are more projective objects in C which are not projective modules. So it depends on this subcategory C. And an object P is a progenerator if first of all P should be projective in C. And for every object X, there exists a short exact sequence from of this form. So there is a surjection from a finite direct sum of this P to X, and we impose that this kernel Y also belongs to C. So actually, these definitions make sense in exact categories in the sense of Theorem. So it's just a rephrasement of these properties in exact categories. And one of the reasons why I started to consider ice-cross subcategory is that if an ice-cross subcategory C has a progenerator, then its ice-cross subcategory can be recovered from this progenerator. So we have the following proposition. And it's very easy to prove. If an ice-cross subcategory C has a progenerator P, then C is equal to the coq of P, and this is defined by the subcategory of mod lambda consisting of cokernels of maps between finite direct sums of P. So it consists of module X such that there exists this kind of short exact sequence. Not short, but this exact sequence. So X is a cokernel of maps between finite direct sums of P. So this says that if ice-cross subcategory C has progenerator, then C can be recovered from this P by this COK operator. And proof is very easy because since C is closed under cokernels, this is clear, and this follows from this for enough projectivity. So for every object, there exists this short exact sequence by the definition of progenerator, and this also belongs to C. So by considering this object, we have this short exact sequence, and then it follows that this sequence is exact. So it means that every object has such presentation. So there is one thing I want to define before moving to next section. A module's M is rigid modules if the self-extension, the first extension group of M vanishes. So by considering progenerator, we have an injection between, so we have a maps from ice-cross subcategories with progenerators and rigid modules. So by taking P, and this is taking progenerator, then it's easy to check that progenerator is always rigid because it's projective object in this categories. So we have this map, and the above proposition says that by considering COK operator, we have the composition of this is identity. So this map is actually injective and this is surjective. So by considering so if if we can characterize the image of this map, then we can establish a bijection between nice ice-cross subcategories and nice rigid modules. And this is the, the main result of today's talk. And actually, we have to divide main result into two parts because in the hereditary case, so path algebra case, for a path algebra case, the situation is very simple and we have a very simple bijection between these ice-cross subcategories and rigid modules. But in general, finite dimensional algebra, maybe one cannot expect such a simple bijection, and instead we use torsion class to study ice-cross subcategory in the next section. So first, I will concentrate on path algebra, and for simplicity, in today's talk, we will only consider thinking quiver. So thinking quiver is just an oriented graph whose underlying graph is simply laced thinking diagram. So this is A3 quiver. And we consider its path algebra. So it's well known that considering modules over path algebra is equivalent to considering representation of quiver Q. For example, for this quiver, for example, representation of the quiver is so for each vertex we put some vector spaces, and for each arrows we put some linear maps. So for example, so so this map. Then this kind of thing is a representation of cube, and there I won't speak detail about this identification, but considering modules over this path algebra is just same as considering representation of Q. Then the representation theory of quiver is closely related to the root system associated to this thinking type. So there is a well-known famous theorem by Gabrielle, which says that we have a bijection between indecomposable KQ modules or indecomposable representation of quiver, indecomposable with respect to direct sum, and positive roots of the associated root system, the root system associated to the underlying graph of this thinking quiver. So in this case, the associated root system is just a root system of type A3. And there is a bijection between indecomposable representation and positive roots. And the maps is given by taking the so-called dimension vector. So for a representation M, its dimension vector is defined by the sum of dimension of this. This is Mi is vector space on I, the vertex I. So for example, this is M1, this is M2, this is M3. And this is the coefficient of this, and this is simple root. So by considering dimension vectors, so we have this positive linear combination of simple roots, and Gabrielle's theorem says that this maps gives the bijection between indecomposable KQ modules or indecomposable representation and positive roots, all positive roots. For example, this A3 quiver, we have this representation, and this corresponds, this is indecomposable representation, and this corresponds to the positive root alpha 1 plus alpha 2 in the A3, the root system of type A3. And for example, the alpha 1 plus alpha 2 plus alpha 3 corresponds to this. And the maps is just identity map. So this Gabriel's theorem gives a connection between representation theory of quiver and the theory of root system of Q. And for thinking quiver, so there in particular, it says that there are only finitely many indecomposable KQ modules. And the classical Krull-Schmidt theorem says that every KQ modules is a direct sum of indecomposable KQ modules in a unique way. So considering KQ modules is just considering indecomposable KQ modules with some multiplicities, which are uniquely determined from the original modules. So indecomposable modules uh, have enough information for considering every modules. And by using this fact, we can prove that, so for thinking path algebra case, every ice cross subcategory of mod KQ has a progenerator. So in this part, we use the thinking assumption, so it doesn't hold for non-thinking quiver. But for thinking quiver, so there are only finitely many indecomposable objects, and by using this, we can prove that every ice cross subcategories has a progenerator. So, this set is just a set of all ice cross subcategories. So the next task is to determine the image of this taking progenerator, this map. But for path algebra case, it turns out that image is just this, the whole rigid modules. And before saying that fact, so we introduce the result of Ingalls-Thomas, which gives classification of torsion class, not ice-cross subcategories. So there exists a bijection between torsion class of KQ. So torse KQ means the set of torsion classes. In mod KQ. And what they call support tilting KQ modules. And the map is just the same as this map. And where M is support tilting, so it's different from the original definition maybe, but so M is support tilting if M is rigid. So the x1 M is equal to 0, and there is some conditions. So this number is equal to the number of composition factors of M. The number of all composition factors, all simple modules up to isomorphism appearing in composition series. And the left-hand side is the number of indecomposable summands, direct summands of M. So in general, we have this equality. So support tilting condition is that first we impose that M is rigid, and then the second condition says that the number of indecomposable summand is large enough. So in general, this number is less than or equal to this, and support tilting ensures that this number coincides. So this is the maybe the first result about classification of torsion classes in the representation theory of finite dimensional algebras. So for example, so before example, I will give first main result of today's talk. This is based on this is contained in my paper, my solo paper, and there exists a bijection between ice-closed subcategories of mod KQ and rigid KQ modules. So this becomes a bijection for hereditary case or path algebra case. So this map, the map is the same, taking progenerators and taking COK of rigid modules. And of course, this extends the bijection between torsion classes and support tilting modules established by Ingalls Thomas. And support tilting has two conditions, but so it says this my result says that the second if we drop the second condition, then we can get all ice closed subcategories. And rigid modules or rigid representation is very natural object, and it behaves well in the viewpoint of homological algebras. So it's a homologically nice modules, and this bijection says that this such kind of nice modules corresponds to certain subcategories closed under images, coconuts, and extensions. And this is a new class of subcategories. So I think I was surprised when I discovered this bijection, because rigid modules is very fundamental object in representation theory of algebras, and this corresponds to new class of subcategories. And I will give example for this A3 quiver. So I don't explain about this so-called Earth-Lambda writing quiver, but this figure represents the category of category mod KQ. So there are 4, 5, 6. So there are 6, and these 6 modules corresponds to indecomposable modules, and the number is the same as the number of positive roots of root system of type A3. And for example, consider these modules. Then it's rigid modules. We can check that there is no extension. Actually, this is because it's projective modules. And then by taking COK operator, we have this subcategory because this modules is a cokernel of this map. And actually, this M is not support tilting because the number of composition factor is equal to 1, 2, 3. So this number is 3, but there are 2 indecomposable summands. So this equality doesn't hold. So M is not support tilting. And actually, this subcategory is ice cross subcategory, but it's wide subcategory in this case. So for thinking path algebra case, so there is very nice bijection between ice and rigid. And actually, so for rigid modules, there is an interpretation using root system or cluster complexes. So I remarked that the number of rigid modules or the number of ice cross subcategories is equal to the number of certain faces. So not the whole face, but certain faces of cluster complex of the associated to this quiver, thinking quiver Q. So by using this, there is an explicit closed formula of this number. And so for type AN case, the number is this sum, n choose I and n plus I choose I. And this is what is called Schroeder number. And and there is a formula for each thinking type. But maybe there are no unified type independent formula is known. And for example, for type E6, there are 4,878 rigid modules. So there are 4,878 I-scroll subcategory in the representation theory of E6 quiver, and maybe you know this number in the Zoom, this thinking type in the Zoom passcode. So I will speak a little about the proofs. And actually, the non-trivial part is that, so we all already observed that we have this map and this map is identity. So the non-trivial part is that for any rigid modules, its COK becomes I-scroll subcategories. So it's a non-trivial part. And non-trivial part is that COK of M is ice for a rigid module K, module M. And this is proved by this kind of thing. So COK is not a torsion class, but not torsion class in the whole module categories, but it's a torsion class in this category. This is the smallest wide subcategory containing M. So it's wide closure of M. So it's the smallest wide subcategory containing M. So COK is M is can be proved to be a torsion class in this category, and this proof uses the theory of exceptional sequences developed by Crowley-Webby and so on for hereditary case. And in general, torsion class of wide subcategories is I-scroll subcategories. And this is very easy to check. And so a torsion class is previously defined in the module category, but M wide, this is wide subcategory. So its wide subcategory is a abelian subcategory in itself. So we can speak of a torsion class in this abelian category. So this is the torsion class of wide subcategory means that's So the proof is the non-trivial part is proved in this way. And so in the proof, actually we proved the more stronger result because COK is a wide portion class of wide subcategory. So in particular, by the proof of this, we can prove that every ice closed subcategory is a portion class of some wide subcategory. And it turns out that this is true for general finite dimensional algebra, and we will see soon in the next section. And so let's move to the next section. And unfortunately, except for path algebra case, maybe it seems to be difficult to characterize, to give an intrinsic characterization of homological characterization like being rigid of progenerator of ice cross subcategories. So if we can characterize progenerator of ice cross subcategory, then we have bijection between ice with progenerators and that class of modules. And for path algebra case, the progenerator of ice is precisely rigid modules. So path algebra case, this is just progenerator of ice is just rigid, and rigid modules is a very simple homological characterization. But for general algebra case, it seems to be difficult to give such easy homological intrinsic description of progenerator of ice cross subcategories. But instead of giving such characterization, we can use the poset of torsion classes. Poset post lambda is the poset of all torsion classes, and the poset structure is just the usual inclusion relation. So, in what follows, we move to general finite dimensional algebra, not only for path algebra, but we consider general non-hereditary algebra. So the key notion is that for such these two torsion classes, if we have two torsion classes such that the one is contained in the other, then we can associate a subcategory which we denote by H, UT. This is defined by the intersection of T and UPUP, where UPUP is a subcategory of mod lambda such that the home from every object in U to X is equal to 0. So there are no homes from U to X. So for these two intervals in torsion classes, to these intervals, we associate these subcategories. So this is a subcategory of module categories, and it we call it the heart of an interval UT. So UT is an interval in the poset of torsion classes. So for each interval, we associate a subcategory defined by this, and we call it the heart of this interval. So it's something like a categorical version of T minus U. For example, there is a trivial formula. So if we consider the heart of interval of the form 0t, then we obtain t. And this is something like t minus 0 is equal to t. And for example, in the consider this path algebra, then the poset structure, the Hasse diagram of this poset torsion class poset is this 5-element lattice. And for example, if this is T and if this is U, then it's just an image illustration, and this the, the difference of this and this is H sub UT. And for example, the difference of this and this is the smallest element, which is 0. So the difference of this is this. So if this is t, then this difference is t. So it's just an image. And why? The reason why I started to talk about heart of intervals of torsion class is that is the following key proposition, which says that if she is an ice cross subcategory, then there exists an interval in the poset of torsion classes such that C is equal to the heart of this interval. So HTU is T cap U path. This observation says that every ice cross subcategory can be realized as a heart of some intervals of torsion classes. So, and in general, the converse implication doesn't hold. There are many intervals whose heart is not ice closed. But all ice cross subcategory is obtained by taking hearts of some intervals. So the natural question is to give a characterization of such intervals UT whose heart is ice closed. And this is the second main result. And to state this result, we recall the Hasse diagram or Hasse quiver of the poset tos lambda. This is the Hasse quiver. Hasse quiver is just an oriented graph whose underlying graph is the well-known Hasse diagram. So vertex corresponds to torsion class. And we write an arrow from T to U if T is strictly larger than U, and there exists no V satisfying this. So T covers U in the poset structure, in the poset post lambda. So this is the standard definition, and maybe the, for example, this becomes this quiver, and note that this one is the largest one. Largest one is always mod lambda, and this one is the smallest one, it's 0. So there are arrows from larger one to smaller one in our convention. Then this is the second main result. This is joint work with Arashi Sakai. And the following are equivalent for intervals of torsion classes. The first condition is that the heart UT is eyes closed. The second condition is a purely poset theoretical combinatorial conditions. So first define U plus as a join of all U primes such that there exists an arrow from U prime to U in Hasek diagram. So I forgot to mention, but this tos lambda is actually a lattice, not just poset, but it's lattice, so we can take join operation. So take the join of all torsion classes such that there are arrow ending at U, then taking the join, then we define U plus in this way. And for this U plus, we have that, and this is always false, but T is contained in this U plus. So maybe we should look at some examples. So if this is U and there are two arrows ending at U, and for example, consider this kind of things, then maybe this is just a local picture. Then the U plus is this. It's a join of these two, and the join of these two is this. So this is U plus. And the second condition says that this T is between this U and U prime. So there are 1, 2, 3, 4, 5 possible choices for this T. So for each, for example, if this is T, then its heart is a one eyes closed subcategory. So this is another eyes closed. So then this is eyes. So there are 6 eyes closed subcategories. Uh, 6 intervals whose heart is eyes closed subcategories. And as you think in this figure, so this only depends on the poset structure of the poset of torsion classes, or lattice of torsion classes. Combinatorial array to construct all eyes closed subcategories if the poset of torsion class is given. So the second condition is just purely possess theoretical conditions. And by this key proposition, every ice-cross subcategories is obtained by this form. So every ice-cross subcategory is obtained by first choosing U, then compute U plus, then for each t between U and U plus, the hard UT is ice-crossed, and every ice-cross subcategory is obtained in this way. So this is actually not a classification because it's not a bijection. This means that for example, different intervals may give same ice-cross subcategory. Maybe this and this give same ice-cross subcategories. So, but as a corollary of this result, we have the following description of ice-cross subcategories. Corollary for a subcategory C of mod lambda. The following conditions are equivalent. The first condition is that C is ice. The second condition is that C, maybe you have already seen this condition, C is a torsion class in some wide subcategory of mod lambda. So maybe the proof of this for path algebra case, we have already saw this condition we have I mentioned before. But for general finite dimensional algebra, the condition that C is closed under taking images cokernels extension is described by this kind of condition. So C is a torsion class of a wide subcategory of mod lambda. So this corollary can be regarded as the composition of, so ice cross subcategory is some this kind of structure. So first take wide subcategories and then take torsion class, then we obtain ice cross subcategory. And the proof that the second condition implies the first condition is very easy and straightforward. And it's just by proof follows from just by considering the definition. The non-trivial part is this part. So if C is ice, then by key proposition, C is equal to the heart of some interval. Then by the main theorem, we have this relation. So T is contained in this U plus. And we have to use another, the result by another people. So we have this, in the poset of torsion classes. And by taking intersection of these and pop U, we obtain this chain of subcategories of HU prime U plus, and HUT is C, and this corresponds to 0 because cap u pub is 0. And actually, this subcategory is wide subcategory. And by this map, we obtain torsion class of this HUT. This result is due to Asai and Pfeiffer's in the maybe 2 years ago in the archive. And by using their result, we have that this C is a torsion class of this subcategory, and this subcategory is wide by Asai Pfeiffer's characterization of wide intervals. So I won't talk in detail, but by using their results, so we can actually prove that every I-scroll subcategory is a torsion class of some wide subcategory. And maybe there are 20 minutes left, so maybe we can move to the next section. So before that, so I will give an example. So consider this past algebra case. Then the module category looks like this. And this is the whole module category. And inside of this, for example, this is wide subcategory. And inside this wide subcategory, this is a torsion class. And this is so this subcategory. And this subcategory is not a torsion class and not wide subcategory because it's not closed under quotients and kernels, but it's closed under images, co-kernels, and extensions. So this is ice closed subcategories. So and every ice closed subcategory is obtained by first take wide subcategories and then consider torsion class of this wide subcategory. And so this this and this theorem gives a way to construct all I-scroll subcategories, but recall that we are considering progenerators of I-scroll subcategories. And so, and this doesn't say about progenerators of I-scroll subcategories, and this is what I want to talk in the next 15 minutes. What about progenerators of I-scroll subcategories in general case? And actually, so since can we have this picture, every I-scroll subcategory is reduced to study of torsion class of some another abelian categories, and we want to consider progenerator of torsion class is in abelian categories. And there is a work of uh, the recent work by Adachi and Moraitens on tau tilting theory. And in this final section, I will describe progenerator of ice-cross subcategory by using tau tilting theory, the language of tau tilting theory. So I quickly remind the related definitions of tau tilting theory. And I remark that this is not the original definition, but this is maybe the most simple definitions for those who don't know Australander writing translation. So if you know Australander writing translation, maybe uh, this part sounds strange, but um, we say that a module is tau rigid if suppose that there exists an surjection from a finite direct sum of M to another module N, then extension of M to N vanishes. So this is a stronger condition than being rigid. Being rigid means just x1 M is equal to 0. But the rigid requires that this x vanishes for every quotient of direct sums of M. From M to every quotient vanish. So this is stronger. And so this implies that M is rigid, and this implication holds for path algebra case. And second, M is support tau tilting, and maybe this is not the usual definition, but uh, M is tau rigid, and the number of indecomposables direct summand of M is equal to the number of composition factors. So the number of simple modules appearing in composition series of M up to multiplicity. So, and as in the case of support tilting modules, so we have this equality in general. So the first condition is a kind of rigidity condition, and second condition says that the number of indecomposable summand is large enough. This is the same as support tilting modules uh, of a path algebra case. Then Adachi and Malraiten established bijection between torsion classes with progenerators and support tau tilting modules. The map is the same, so by taking progenerators and by taking co-kernels, and maybe some of you notice that this is not the usual description. Maybe we usually describe this part as functorially finite torsion class, but this condition is equivalent to being functorially finite. And this COK is equivalent to fac of, support rotating modules in this case. Anyway, we have this bijection, so there is characterization of progenerator of torsion class. It's precisely support rotating modules. And maybe this is uh, homological characterization. And recall that so for simplicity, assume that the number of torsion classes is finite. And we name this assumption star for simplicity. The following is just, we assume this for simplicity. Then, if this condition is satisfied, then every ice closed subcategory has a progenerator. And every wide subcategory W is equivalent to another module category for some finite dimensional another K algebra gamma. And maybe we are able to state our final result. So now recall that C is ice if and only if C is a torsion class of some wide subcategory of mod lambda. And under the assumption star, this mod lambda, this W is abelian category, which is equivalent to another module categories. And since this is the torsion class of module category mod gamma, then and this C has progenerator, and so we can use the tau tilting theory for this category. So this is what we call wide tau tilting modules. A module M, lambda module M is wide tau tilting if there exists some wide subcategory such that M is support tau W tilting. So tau W tilting means that since W is equivalent to module category, so we can speak of tau tilting gamma modules. And this says that M is tau tilting support tau tilting gamma modules under this equivalence. So this is maybe not straightforward or not this is complicated definition because we have to designate some wide subcategories. So it's not interesting homological characterization. But so then, but if we adopt this, we use this notion, then we can state our final bijection. So assume that there are only finitely many torsion classes. So this assumption is a rather strong assumption, but there are many, many examples which satisfy this. For example, the thinking path algebra case or pre-projective algebra of thinking type, or there are many lots of examples. Then, and maybe this theorem is easily follows from the definitions and some investigations. And by assuming this star condition, then we have a bijection between ice-closed subcategories, and by taking progenerators, we obtain wide tau-tilting modules. And the COK of wide tau-tilting modules is ice-closed subcategories, and these two maps are mutually inverse to each other. And actually, obviously, this extends the bijection between torsion class and support tau tilting modules. So we can extend Adachi-Yamamura-Raiten's bijection between torsion class and support tau tilting modules to ice cross subcategories and wide tau tilting modules. And final remark. So as we saw before, for path algebra case, everything is very simple and nice because wide tilting module is just rigid KQ modules. So we don't have to care about these wide subcategories. And this is nice, very nice, because KQ is hereditary algebra. But in general, we have this. And maybe I haven't uh, give maybe uh, we haven't characterized wide tau-tilting modules in a simple homological way so far. Maybe it's interesting but difficult problem, I think. And so now finally, let's look at some example in our this example. The module category looks like this. This. And we have seen that this is ice. And the corresponding wide tau-tilting module is this and this. And this is actually consider this to be W. And we have seen that this ice cross subcategory is a torsion class of this wide subcategory. And in this case, this the direct sum of this and this is wide tau-tilting modules. And maybe the time is over, so I finish here. So thank you for listening.